High intensity means that we can irradiate tumors in a flash, in a few milliseconds. And higher energies means that we can simulate much better the cosmic rays and to understand much better the risk of astronauts in long-term missions like a mission to the moon or mission to Mars.
Welcome to Chelonia Podcast, a podcast about the use of scientific discovery and of technology application. We provide the best information on projects participated by Chelonia and many more. My name is Gabriella Bernardi, I'm a science journalist, and in today's episode we talk about atoms, cancer therapy, and cosmic rays with Marco Durante, Professor of Physics at the Technical University of Darmstadt and Director of the Biophysics Department of GSI Helmholtz Center of Heavy Ion Research. Nice to meet you, Professor, and would you please introduce yourself and tell us something about GSI and your role?
Thank you very much, Gabriella. So I'm a physicist. I graduated in Naples at the University Federico II in Naples. And then I have spent, however, most of my career abroad because first I was in Berkeley for my PhD. Then I was in Houston working for NASA, Johnson Space Center. Then I was in Japan working for the National Institute of Radiological Sciences in Japan. And finally I landed in Germany here, where indeed I have the honor to be the director of this important center that was founded by Gerhard Kraft, who is a very well-known physicist, and is very famous in our field because it was the first center in Europe to treat patients with accelerated carbon atoms. This is a technique that was already used in Japan, where I was for my postdoc, but Gerhard Kraft was the first one to use it in Europe. Since then, we have no more patients. We are completely focusing on research, and we are part of the Helmholtz Association, which is in Germany, is a network of infrastructures, essentially, similar to Max Planck, but is more based on the infrastructures.
From atoms to cancer treatment, how did you end up in your role?
Yeah, that's an interesting, intriguing question, because I was, I was trained as a nuclear physicist, but then, of course, I was always fascinated by medicine and biology. In fact, when I chose my faculty, I was not so sure whether I should be biology, medicine, or physics. At the end, I'm a lucky guy because, I have the opportunity to work in a very interdisciplinary field. My group is almost 100 people, and they are physicists, biologists, chemists, engineers working all together.
So, GSI facility is famous for its discovery of 6 elements in the periodic table with a ephemeral life of few milliseconds or less. Why it is so important?
Right, of course, GSI is very famous. We have these elements. If you look at the periodic table in the bottom, you will see elements with that are named like Darmstadium from Darmstadt or Hessium from the state of Hessen where we live. Of course, you will never see a block of Darmstadium on your desk because, as you say, the average lifetime of these elements is extremely short. But from the nuclear theory, these experiments are extremely important. So we want to add protons and neutrons to the nuclei to find, let's say, the properties of the nucleus. How, of course, the nuclei are the basis of everything in the universe, and the problem is how heavy they can be from the point of view of the forces. Because, of course, the problem in creating a nucleus is that you have protons that, if they come together, they will have a strong repulsion because they are two positive charges. So in principle, they should not stay together. to keep them together, especially when they are heavy, you need many neutrons, because neutrons have no charge, but they have this nuclear force, which is a short-range force, which is like a glue that keeps the nuclei together. So to understand the structure of the nuclei, we need to add more and more nucleons and to see what is the maximum possible element. I mean, there is discussion on whether there is a maximum, whether there is a maximum element, and beyond that element, it's impossible to have a stable for a few nanoseconds. But even there, if it is possible to have it.
Perfect, Professor. GSI is also famous for cancer therapy. Which are the differences or similarities with the other center of oncological treatment?
So let's say more than 90% of cancer patients are treated with X-rays. This is radiotherapy. So you use X-rays for treating patients. But the problem of X-rays is that they are exactly like light. You know, if you have a light, and it's an intense source of light, like the sun, you put the shield between yourself and the light, and the intensity decreases. This we all know. Same thing with X-rays. When they enter in the body, the intensity will decrease with the depth of the body, actually decrease exponentially. You know, it's an exponential function. But the problem is that tumors are deep. So you lose this energy in the normal tissue and not in the tumor. On the other hand, the charged particles, accelerated particles, are much better here, because when they enter the tissue, they are very fast. They come from the accelerator, they are very fast. And when they are very fast, they have no time to interact with the atoms in the body. But they interact a little bit, so they lose a little bit of energy until when they are really slow. When they become really slow, then they can interact with all the atoms, make a lot of ionizations, and you have what is called the Bragg peak. The Bragg peak, which is named by a physicist who was actually Australian, but he worked in UK, William Bragg, is the reason why we like this therapy so much. So you have a higher dose to the tumor than to the normal tissue, which is the key to kill a tumor, because you can always kill a tumor with an appropriate dose of radiation, but the problem is that you don't want to kill the patient. So the dose to normal tissue must be lower than the dose to the tumor.
Very interesting. In June, the GSI conducted an experiment that involved coronavirus irradiation with heavy ions. Will you tell us more about this experiment and its importance?
This is a brand new idea, of course, that came with the pandemics of COVID-19. One way to produce vaccines, as everybody knows, is to inactivate the virus. So you use inactivated virus. Actually, before these pandemics, all vaccines were done with inactivated virus. However, general inactivation is done either by chemicals or by gamma rays. The problem of this inactivation technique is that not only you kill the DNA or RNA, in the case of coronavirus, inside the envelope, but also the external proteins. For example, the famous spike proteins that now everybody knows. And then, of course, you need the spike proteins to be able to elicit a specific immune response against the virus. So we thought that it could be much better to use heavy ions, because in the case of heavy ions, it's like shooting a bullet through the virus. You know, you make a hole in the entrance, you make a hole in the exit, you kill the virus, but essentially you will have very little damage to the envelope proteins. So we did this experiment with the Helmholtz Centrum for Infektionsforschung in Braunschweig, who is another Helmholtz center, but specialized in vaccine development. And we already got some preliminary results showing that our hypothesis is correct, so that indeed we can get a very effective material by inactivating virus with the heavy ions that can elicit a strong immune response.
Closer to GSI, FAIR will be a new facility in 2025. Can you explain why it wasn't decided to be built and if there is something similar to it in the world?
So yes, let's say FAIR is the natural evolution of GSI. You know, GSI is a large accelerator. The accelerators are defined by their magnetic rigidity, because their magnetic rigidity means what is the energy that they can accelerate for which elements. At the moment, the accelerator at GSI is 18 Tesla meter. The next one will be 100 Tesla meter, so much bigger. And the current accelerator is the injector of the new accelerator. So it will be a step ahead. This accelerator is unique for two reasons. Very high energy heavy ions. If you compare to CERN, for example, CERN has higher energies than FAIR, but is mostly for protons. You can only accelerate protons. And generally it's beams that collide between themselves. In GSI instead, at FAIR, we will have very heavy ions at very high energy that collide on fixed targets. And intensity, of course, there will be a large upgrade in intensity up to a factor of 100 as compared to the current intensity. Of course, with this very high intensity, you can do a lot of new physics. So the primary goal of FAIR will be actually to study important reactions for nuclear astrophysics, to understand the origin of these elements, to understand the structure of the nuclei, as I said. We will work on radioactive ion beams, but of course also for us in biomedical applications there are large advantages. High intensity means that we can irradiate tumors in a flash, in a few milliseconds. And higher energies means that we can simulate much better the cosmic rays and to understand much better the risk of astronauts in long-term missions like a mission to the moon or mission to Mars.
In fact, radiation does not come from the Earth only, but cosmic rays can be a source of high energy radiation exposure too. What kind of risk do they involve, and what are the implications for human activities, like, for example, the space exploration?
So, the space radiation is today considered the main showstopper for long-term missions. You know that now it's not only the national space agencies that want to go into deep space, but also private, like Elon Musk or Jeff Bezos. But they all have to acknowledge that if we don't solve the problem of space radiation protection, this endeavor is a high-risk endeavor. Of course, the risk of radiation is cancer, is a typical risk, but also normal tissue effects like cardiovascular disease, brain lesions, and of course also hereditary effects that eventually can occur. The problem of space radiation is that, as I said before, it's very high energy. Being very high energy is very difficult to shield because they are very penetrating, they are very fast. So you need very thick shields to stop the cosmic rays, which are impractical for a spacecraft because, as you know, the most expensive part in the spacecraft is the weight. So you have to keep the weight of the spacecraft as low as possible. So we are committed at GSI with the European Space Agency to simulate these cosmic rays on Earth. So we have a simulator of the cosmic rays, and we are doing both physics and biology studies. Biology studies to understand the risk, to see how severe can be the risk, and physics study to develop new materials for effective shielding during space travel.
You were also president of the International Association for Radiation Research. You can explain us what are the goals of this organization?
Yeah, the IARR, International Association for Radiation Research, is an umbrella organization, let's say, that puts together all the national radiation research organizations. It's These associations are always useful because it's a forum for the scientists to exchange information on a worldwide basis. The topics are all the topics related to radiation research. So of course, topics like I said, that are more related to heavy ions, but also more conventional topics related to radiation protection, like radiation protection for nuclear waste management, or any kind of radiation protection activity, as well as radiation therapy with conventional X-rays. Radiation is always a sort of double-edged sword. On one hand, it's risky because everybody is afraid of radiation because that there is a health risk if you are exposed to radiation. But on the other hand, there's a benefit because you can harness radiation, you can use it to cure disease like cancer, and now also some non-cancer disease. Recently, radiotherapy has been used also for heart disease, for heart arrhythmia. Now there are more and more tests for using radiotherapy for ablation of specific regions of the heart that cause arrhythmia.
So, Professor, what is your biggest challenge right now?
We have two big challenges. Let's say one, as I said, one in space and one in radiotherapy. In space, we want to make the trip to Mars safe, and to do that, we believe that we need new shielding material. We need effective shielding materials, very light materials that can very effectively shield the cosmic rays. And for radiotherapy, we want to make the therapy with particles, with heavy ions in particular, cheaper and more effective. So these are now our big challenges.
Professor, we are at the end of the podcast, so a little curiosity. If you could go back or forward in the time, what would you like to know or discover?
That's also a very interesting question. I mean, for sure, if I go forward in time, I would like to be in the time where we will defeat cancer forever. That's something, I mean, for a person like me and many others, of course, that has the whole family that died of cancer, my parents, my relatives, I mean, unfortunately, but of course, it's not only me. I mean, many people listening have seen similar experience. We would like to see the day when we can say that there is no more, that cancer is no more a lethal disease, that people can live longer and healthier and without cancer. And of course, I would like to see the humans on Mars, which is something I'm not sure I will be able to, though I don't know if this will happen in my generation, but that's definitely something I would like to see. And if we can contribute with the more effective space radiation shielding for a safe exploration, I would be simply delighted.
Thank you so much, Professor Durante, for joining us today at this podcast, and thank you, our listeners. If you have any questions about today's show, you can get in touch on Chelonia Twitter, and feel free to subscribe chelonia.swiss website and be part of the community. In the meantime, stay tuned for our next interview. Thank you.